Howdy folks. So, just following our last video set on Lewis structures and the like, we're going to go into molecular orbital and bonding theories for this chapter. This first video is going to be all about VSEPR models and how we can use it. So this first video is the far more practical from a general chemistry side. The video that will follow this will be a little bit more theoretical, but also very useful from an organic side and understanding why things actually occur. It's more a mental thing than something you can easily hold in your hand. Well, let's go ahead and get started because this first part will be a little bit longer, at least a few more slides. Okay, so it's one of those chapters where you literally need spatial reasoning. You need to be able to picture things in your mind and turn them around and rotate and do all that fun stuff, which is why I say first-person shooters. Because anything that you're looking at, you're moving your character in first person, you have to understand how the controller relates to your character and how rotating him this way or that way makes you turn, look up, look down. So being able to do that on a game system should also apply to being able to rotate molecules. But let's go. So Lewis structures are essentially a good way to understand our bonding, but they really kind of suck when it comes to understand the molecular properties. Because the Lewis structures just need to show what bonds are present. They don't need to show how things fit together. So consider these three isomers of C3H8O. That isomer means it has the same chemical formula, different bonding arrangement. Just based on the structure, all carbons have 4 bonds to them. All oxygens have 2 bonds to them. All hydrogens have 1 bond to them. So nothing is really special here except how they're stuck together. By changing the position of the oxygen, the properties will change drastically, particularly the flash point, which is the temperature above which the vapor, which it's always low-grade boiling. Most things will vaporize at room temperature, even water, just the amount is small. Well, it's the temperature which the vapor will ignite, provide an ignition source. So if you have like an open fire nearby, it's going to go up, even if you don't touch the fire to the liquid. So, and propanol. That's essentially, you talk about that, this being 1 propanol, but it's the linear chain of a 3-carbon alcohol. The density is 0.803. It is by far the most dense, meaning you can pack the most molecules in to the same volume. Its melting point is the lowest, meaning it takes the most amount of energy. Well, it takes the least. Well, I'm trying to think how to. It takes the least amount of energy to melt it. It will melt a lot sooner than everything else. Its boiling point is also the highest. So it melts the easiest and it boils the hardest. So it's going to spend the least amount of time in the liquid, in the solid or gas phase. It mixes very well with water. It's miscible, meaning it dissolves in an infinite amounts of water, and its flash point is the highest at 22 degrees C. So it's the hardest to spontaneously combust. Isopropanol. So I've just moved the alcohol from the 1 position to the 2 position. So 2-propanol and the density has dropped. The melting point has dropped to the lowest, or to the highest melting point of all three, meaning that it takes the most amount of energy to melt. And the boiling point is significant. It's lower than N-propanol, but high, much higher than our ether. It's also miscible, but our flash point has dropped down significantly from 22 to 11. Then methoxyethane. The density has dropped a little bit further, so it's a little bit bulkier. And this is, we've changed from a alcohol poking out the side to just a oxygen embedded between those two carbons. So we no longer have an OH bond, we have a CO and a COC bond. The density is dropped down, so it's the least dense, meaning the most bulky. Its freezing point is relatively low, but it's between the two. But the boiling point is incredibly low at 7.4, so meaning it takes very little energy to vaporize this. It doesn't want to stick together. It doesn't want to stay in the liquid. And even though it has an oxygen, which we'll learn is very polar, it is insoluble in water. It doesn't want to mix with water. And its flash point is incredibly low at negative 37.2. So any normal freezing, any normal temperature we would experience in a room, if there is a flame, that is bursting in. If the flame open, it's bursting into flames. So all that by just changing the arrangement of that oxygen. If just based on the Lewis structure alone, you're not really going to get a full picture of what's going on. That's why we need to start moving into 3 dimensions. Understand why putting the oxygen at the end versus the oxygen poking off in the middle versus the oxygen embedded versus the carbons, how that can have such a big change in our properties. So to do this, we're going to need what we call VSEPR models. VSEPR stands for Valence Shell Electron-Pair Repulsion Model. So valence shell means we're using the valence electrons. We're not caring about the core, we're only looking at the valence. Electron pair means we're working in electron pairs. We're not doing individual electrons, we're looking at paired electrons either as lone pairs or as in bonds. And repulsion is going to be the theme of this model. That electrons are negative and they want to repel other electron pairs. And so we're going to make a model that emphasizes the repulsion. So when we look at our model, the overall shape of our molecule is going to depend on a number of individual unique electron domains. A domain or domicile is the home. The electrons, where the electron's at home within this Lewis structure. It's the region of electron density where a pair is located. Probabilistically, where is it most likely found? So if it's found in an orbital floating as a lone pair, that's going to be a location. If it's found between 2 atoms in a bond, that's its location. So it does not care whether this is a bond or lone pair. It's saying where this is a region where electrons are located and they can't really move. So we're going to lock them in and base our structure based on the number of electron domains. I know the electrons are capable of moving within that little probabilistic region of cloud, but we're going to treat these like kind of a stationary arm, the place where they can, I'm holding on to something and moving it around. Now, normally these orbitals like the S, the P, the D orbitals, are rigid and located in space. But we're going to treat these guys as there's like a cloud of electrons capable of being shifted with respect to each other, like clouds blown with the wind. You can blow it this way, you can blow it that way. Well, these electron clouds are going to move in such a way that they are going to maximize their distance away from each other. So normally the p orbitals, oh, okay, these guys are going to be 90 degrees apart. Well, that's not always going to be the best location. So it's going to adjust itself so that the electrons are farthest away from each other. Now, due to the charge repulsion, the basic idea that electron clouds repel each other, these molecules will adopt shapes that reduce the total amount of repulsion in order to get the most stable structure. And this stable structure, based on the maximum distance apart, based on the electron domains, and only the electron domains, is called the electron geometry. So when we're looking at just the electrons in their pairs, it's the electron geometry. Now, one thing we will need to recognize, even though I will rarely, if ever, ask you to calculate this, is that we are going to adopt bond angles. A bond angle is an angle made up between three atoms, with the center atom being between the two outer atoms. So we're saying, what angle does atom A make with atom C, with atom B being in the center of that? Now, these same angles are defined in similar ways as what we might be defining with a circle. The maximum bond angle would be 360 degrees, but once we start looking at that, once we hit the halfway point, you could also look at the angle from a different side. So once we get past 180, even though it would be 185, you can also look at that as 175 from the other direction. But so just like a circle, these angles are going to top at 180 and then head back down the other way. But we're going to try to minimize electron repulsion by maximizing these bond angles. So if I have two atoms off the center atom, the furthest they can get away from each other is on either side. The bond angle between them is 180. Split a circle in half, you have 180. Well, you split a circle in thirds, you're going to make 120. You're going to make 120. There's no other way to do that other than make 120. And that's what the picture we see right here. Now, normally if you split a circle in fourths, you would say, well, there's 95. However, a circle assumes we have a flat plane. In reality, we have all three dimensions available, and so we adopt a shape that looks like this. Looks like this. And this shape, each bond angle is 109.5. We have 3 going down and 1 going up, and we'll see more of that later. If we adopt 5 atoms, 5 atoms off the center, we adopt a shape like this. It's the triangle. It's our triangle plus 1 up and 1 down. So we get 120 from the triangle and 95 to each the top and bottom. Finally, if we add 1 more atom, so a total of 6 atoms off the center, everything gets smushed to be 95. Everything gets smushed to be 95 degrees off from each other. So these are the maximum bond angles we can achieve here. So generally speaking, here are the basic shapes. Say, note the bond angle. So what are we talking about? So in this little diagram, we have the steric number. Steric number refers to how many atoms off the center atom. X are used to just say the outer atoms, with E being the center electropositive atom. And so we're saying with 3 atoms, the best way we can make a geometry is 180 degrees, and we call that linear. Linear. And when we have 4 atoms, 3 coming off the center, we have trigonal, planar, breaking down a flat triangle, trigonal, planar. Note in this guy, wedges and dashes. Wedges and dashes are used to show 3-dimensionality of either coming towards you or away from you. Dashes are moving away. Wedges are typically coming towards you. Any line that is flat line is assumed to be flat on the paper. So when we have 5 atoms total, 4 around a center atom, we have tetrahedral. Called tetrahedral because it makes the shape of a tetrahedron. Essentially a equilateral triangular pyramid. Equilateral triangular pyramid. Equilateral means each triangle face of this pyramid is the same shape. So if no matter how I rotate this pyramid, each face is identical. So I could flip this on its side and it would still be identical. So it's an equilateral pyramid. Essentially like a D4, if you've ever played a game that uses a 4-sided dice. That ideally, no matter how you roll this, there's equally probability of getting any of the 4 numbers. Tetrahedral because there are 4 faces. Now we look trigonal bipyramidal. If you connect these lines, you have a triangle. But if you draw them up to the X, you get a pyramid, a triangular pyramid. But if you draw them down, you also get a second inverted pyramid. Thus the name trigonal bi meaning 2, like bicycle, pyramidal. Trigonal bipyramid is a doubled triangular pyramid. And finally, octahedral. Notice we have 2 sets coming forward, 2 sets going reverse, and 1 up and 1 down. This, if you connected all the dots, would be a square bipyramid. So it's a square pyramid, but it's going up and going down. It is essentially, in dice form, a D8. There would be, you would make 4 sets of pyramids going up to the top X, 4 sets of pyramids going down to the bottom X. So it is uniform in that the top and the bottom are identical, and that it's octahedral, meaning even though there's 6 atoms coming off the center, they make 8 faces. 8 faces, thus the octahedral name. With practice, some of these will make more sense, but until you start to do it, it becomes hard to kind of remember all the names. But the names do make sense. Octahedron is an 8-sided figure. Octahedral, 8 sides. So how do we determine the electron geometry? Step 1 is we just draw the most stable Lewis structure. That's all. You draw the most stable Lewis structure. Now, does it matter where all the double bonds are? No. It doesn't matter if it has multiple resonance structures. You draw the most stable Lewis structure, and we're going to go from that. Now, we only ever care about the central atom. We're only going to base our geometry based on the central atom. So it doesn't matter what the geometry would be from the perspective of the outer atoms. We only really ever care about the geometry from the central atom. So we count how many regions of bonding and how many lone pairs are coming off the central atom. Note, I said regions of bonding, not the total number of bonds. So, the number of these will be the electron domains. So, in the example down there with nitrogen, N2, we have a triple bond and a lone pair coming off any single nitrogen. Well, that triple bond counts as one region of bonding, not three. So one lone pair, so this means this guy has two electron domains. It would be linear. Well, what about BEH2? Well, there is two BEH bonds coming off the center BE. So it is linear. CO2, even though carbon has 4 bonds, there is 2 bonding regions. Double bond number 1, double bond number 2. This is linear. And an OCN, or you could say CNO, however you want to say that, however you want to give it, there is a triple bond and a single bond. Well, that guy has one triple bond, one single bond, 2 regions of bonding density. And then here's the brilliant part. You could draw a resonance structure for that. It may not be the most stable resonance structure, but it is one where you have a double bond to nitrogen and a double bond to oxygen. You may have changed around the formal charges, but how many regions of bonding are coming off the carbon? Still 2. If I drew the least stable resonance structure with a triple bond to oxygen and a single bond to nitrogen, there's still 2. 2 regions of electron density coming off the carbon. It still remains linear regardless of the resonance structure you may draw. That's why it does not matter. You're just drawing a Lewis structure. Now, with that in mind, 2 electron domains means it's linear. 3, trigonal planar. 4, tetrahedral. 5, trigonal bipyramidal. And 6, octahedral. These basic shapes will maximize the distances between our electron domains. So, now, all that's good for a start. However, bonds and lone pairs will have a bigger difference when it comes to reactivity. Bonds versus lone pairs. They both contribute equally when finding an electron domain, but when it comes to reactivity, their properties are entirely different. So for that reason, we will look at another way of determining the shape. And for that, we are going to call the molecular geometry. The molecular geometry looks at the shape of the bonded atoms and ignores the lone pairs. They're still there, they're still active, but we're looking at the shape created by the nuclei, not the lone pairs. So in reality, the molecular geometry is just a modification of our electron geometry. So we're still going to find the electron geometry first. We always need the number of electron domains to start with. But then we are going to take the number of bonding domains, so regions where there's bonds, and compare this to the regions where there are lone pairs. We're going to create a modification of our shape based on the difference between the bonding regions and the lone pair regions. The shape that we're going to label it will only consider the bonds, but that doesn't mean the lone pairs are not there. They're still there. In fact, in the shapes themselves, the non-bonding electrons will take up more space. Since they are not constrained between two atoms, since they don't have a bonding region that they have to stay in, they can kind of spread out. So non-bonding electrons actually take up more space, and it's going to distort and squish all of the bond angles with regard to the bonding regions. However, remember, we always start with a complete Lewis structure first. Then then we find the electron domains, and we need to then find bonding and lone pairs. We always want to draw the Lewis structure because if I give you CO2, I don't know what the central carbon looks like. Well, I do, but I mean, you may not know what the central carbon will look like. If I say NH3, you don't know that center nitrogen has a lone pair until you draw it out. If I give you water, with the H2O, where there's two things coming off of oxygen, is it linear? No, because there's two lone pairs. And you have to draw these out to make sure you know where the lone pairs are. Make sure you know there are lone pairs. It's not always obvious unless you are well versed in this lore. So here are all of our shapes. Please note, some of these options have more than one name. Either name is equally valid. You don't have to use both. But so it's where we took away one of the outer atoms and replaced it with the double dot, which is our lone pair. So if we linear, still stays linear if you remove one of the outer atoms. Trigonal planar, if I remove one of the outer atoms, it becomes bent, or you could call this angular. It's not a triangle, but it's not a line. If I have tetrahedral and I remove one of the outer atoms, no matter which outer atom I remove, it becomes a trigonal pyramid. Trigonal pyramid, which basically means instead of the equilateral structure, it's a smooshed pyramid. It's a triangle, but now it's an isosceles triangle with the peak being at the E rather than being at the upper X. So if here was our big pyramid, we're smooshing it down to a smaller pyramid. And if we remove a second atom, regardless of whether we move it, where we move them, it once again becomes a bent structure. Water is a bent structure. Ammonia is a trigonal pyramid structure. When trigonal bipyramidal, because of the nature of the lone pairs, that the lone pairs want to take up the most space, this is going to control where I lose the atoms from. So the first atom I lose is from the triangle, and so it becomes a sawhorse or a seesaw. But the basic idea here is you've turned this on the side, you can see the two of the wedge and the dash structure becomes the wobbly base, and then we have more or less straight structure for our the platform for the seesaw or the platform for the sawhorse. If I remove a second atom, don't think I removed a different atom. I removed that second atom from the center triangle. I've just now spun it around so we can better see it. If I take this atom and this atom, I can rotate this until I get that remaining X right there, just so I can better see this. This is a T shape. See, it's T. It's a long cross, but it's basically a T stop. We call that T shape. And if we remove a third atom, it's all from the triangle, and it goes back to being linear. Goes back to being linear. The octahedral, it doesn't matter where we remove this atom. I show it being removed on the bottom, but any location can be removed, and we can rotate it to make it look like this. So previously there is a square pyramid up and a square pyramid down. The octahedral is the square bipyramidal. And so when we remove the one atom, it loses the bipyramidal part, and so it just becomes a square pyramid. Now, since lone pairs take up the most space, we want to keep the lone pairs as far away from each other as possible. So the first guy we remove, it doesn't matter. The second guy we remove should be as far away from the first guy as possible, so it's on the exact opposite side. And so we remove the part that makes it a pyramid, and it's now just a square. It becomes a square planar structure, meaning flat square. The third atom we remove doesn't matter, because any atom we remove at this point is not opposed by any other atom, and we can rotate it. And so we have 3 atoms left, and it becomes a T shape. And the fourth atom to be removed, if we remove a fourth atom, has to be opposed by the previous lone pair, so it becomes linear again. So we can always adopt and look at this chart whenever we're doing this, but if you just draw it out and figure out the basic geometries and just modify it, it's very easy to understand. Now, how would you read this? So we got the steric numbers, which is the number of electron domains. We start off here with 0 lone pairs for our electron geometry. And then depending on the number of lone pairs, we're going to shift it over that many steps and correlate on the table what is its new shape based on the number of lone pairs and its electron domains. So we're going to run 2 quick examples of how would we go about doing this. What is the molecular geometry of these 3 shapes? Now, these 2 shapes. Now, you may want to just go, okay, well, xenon tetrafluoride has 4 things coming off xenon. It must be tetrahedral. Chlorine trifluoride has 3 things coming off the chlorine. It must be trigonal planar. But that isn't always the case. Don't just assume. You have to check. So, Lewis structures, rules. 8 from xenon. 7 from fluorine. There's 4. So 7 times 4 is 28. So 28 plus 8 is 36. Doesn't have to be pretty. So we go xenon in the center. F, 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 F. That's 8. We're down to 28. We have to go 6 on each one. 12, 18, 24. Now here's the important part. Here's the most important part. We have 4 electrons left. Where do those 4 electrons have to go? They have to go on the center. There we go. Now, this is the Lewis structure we want. Yes, xenon has an expanded octet. Is that okay? Yes. So how many electron domains? How many things are coming off the xenon? So I'm going to count them. 1, 2, 3, 4, 5, 6. 6 electron domains. So that means my xenon has 6 things coming off of it. So I'm going to draw the basic structure of that. I'm not going to fill it in just yet. That's octahedral. Octahedral. However, how many lone pairs? 1, 2. So I'm going to fill in 2 of them as lone pairs. The rest being fluorines. So what is this shape actually? Too many. This shape is actually square planar. Square planar, and that it adopts a flat square. You would not necessarily get that just by looking at xenon tetrafluoride. Chlorine is 7. F is 7. 7 times 3 is 21, so we have 28 electrons. Chlorine, 1, 2, 3. It doesn't have to be pretty. That's 6 electrons. That gets it down to 22. 6, 12, 18. 4 left. Once again, slap them any old where. Don't really matter. Don't really matter. Lewis structure doesn't have to be pretty. Doesn't have to be pretty. Electron domains. 1, 2, 3, 4, 5. 5 electron domains means it's trigonal bipyramidal. So let's draw that structure. Chlorine, wedge, dash, chlorine, wedge, dash, line. Now, how many of them are lone pairs? 1, 2. So, we put the lone pairs here. F, F, F. And it becomes our T shape. It's T shape because it's adopting the T. You would not necessarily see that right away without drawing that out. Sometimes it's obvious, sometimes it's not. H2CO. Sometimes it doesn't matter. I'm going to do one more. C, 1 plus 1 plus 4 plus 6. Sometimes they are what they are. So that's 12. Put the C in the center. O, H, H. That uses up 6. We got 6 left. We have to put them boom, 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 boom. 0 left. Well, I can then take 2 away and make a double bond. However, that does not affect my numbers. 1, 2, 3. 3 electron domains means it's trigonal planar. 0 lone pairs means it stays trigonal planar. What if I did PCl3? Actually, I'll do pH3. I'll just make my life a lot easier. pH3. 5 plus 1 plus 1 plus 1. That's 8. They're not always going to be this easy, but so H, that uses up 6. 2 left to place. Slap them on the center. So we have 1, 2, 3, 4. 4 electron domains means tetrahedral. But wedge dash line. 1 lone pair means we put that there, and the rest is trigonal plane. Oh, trigonal pyramidal. Trigonal pyramidal. So being able to do that is a useful thing to do. Help us understand these things. Now, we will not always be blessed with small molecules. We can look at large molecules. However, all you need to know is that large molecules are made up of small molecules. Molecule gets more complex, the overall shape is harder. We can't just describe this one molecule as having a one shape. However, each part of the chain, each central atom of the chain, will adopt one of our basic geometries. We have on the bottom left acetic acid. Acetic acid, the key component of vinegar. The carbon 1 on the farthest left is adopting a tetrahedral shape. Note the 4 electron domains. Carbon number 2, the gray carbon that's attached to the 2 oxygens, is adopting a trigonal planar shape. Notice the 3 electron domains. The red, or the pinkish little nodules are lone pairs. So the oxygen with the OH and the 2 Mickey Mouse ears is adopting a bent shape. Bent because of 2 lone pairs and 2 bonding pairs. The structure over there is, I think, tyrosine, a simple amino acid. Amino acid means it has an acid moiety and ammonia moiety, so we can see the same trigonal planar bent shape out of here. Over here it's tetrahedral. The ammonia part is trigonal pyramidal because of the 1 lone pair, and each part of this ring, because it has 3 electron domains, is trigonal planar. So this whole thing is planar, even though we have this guy's kind of funky looking. Amino acids will all fit together based on different interactions, but also based on their shapes, how pokey and how much they come out. Now, why is this really important? It's because all these molecules, all these proteins, come together in certain ways. Hemoglobin, which is the key component in our blood, the oxygen binding protein in our blood, is made out of 4 individual globin proteins. Each contains a basic molecular unit called a heme. There's a lot of funkiness going on, but you can see in here the 4 green little hemes. Each globin contains just 1 heme. The heme fits perfectly in there and binds to iron, leaving a space for oxygen, or in the case of the deadly carbon monoxide, to bind onto it. So binding in 1 heme actually causes the shape to change of the overall protein, so it makes it actually easier for further oxygens to bind. So the more oxygen you have, the easier it is for hemoglobin to take up the maximum quantity of oxygen. And we can see that moiety. You can look at this. This guy ends up being more or less planar, based on everything being essentially a kind of a trigonal, the 3 electron domains coming off of it. So all proteins will utilize this molecular geometry and shape-based intermolecular interactions to make essentially an active site or reactive pocket in the molecule for another atom to fit. A hydrolysis creates a pocket so that it holds the molecule in a way that it can cut off water very easily. Lyse means to cut. So this is the space-filling model of the hemoglobin. Notice how it's more or less flat. See that here the iron is able to bind the oxygen up top. If this was Not planar, oxygen would have a harder time approaching and a harder time binding. But so this is kind of important. There's a lot of people who do a lot of molecular modeling to understand how these proteins will fold and fit together, but it all comes down to three-dimensionality of the shapes and how they can fold and bend around their bonds. Now the last thing I'm going to talk about for this video has to do with polar molecules. So earlier in the previous video we looked at the concept of dipoles, the individual polarity of a single bond. Well, now we need to consider the overall dipole of a molecule that makes up a molecular dipole. Now to do this we need to understand the concept of vectors and opposing forces. A vector is just a force given dimensionality. It's all well and good to say I'm traveling at 60 miles an hour. That is a speed. But to say I'm traveling 60 miles an hour north gives me a velocity. It gives me a vector of I'm traveling at this speed in this direction. Well, if I hit someone traveling at 60 miles an hour going south, we're probably going to stop. Though if there's someone traveling 60 miles an hour north after me, we are not going to interact. So understanding vectors and how they could oppose each other, we need to understand how these vectors fit in a 3D coordinate system. Now, take for example, if I'm traveling 30 miles an hour north and someone's traveling 60 miles an hour behind me, they will catch up and possibly bump me forward a little bit faster. If I'm traveling 30 miles an hour north and someone's traveling 60 miles an hour south, when they hit me, they'll probably push me backwards some because they're moving at a faster speed. So we can understand this as a dipole. We need both to understand how the strength is pulling one way or another, not just the direction, but also the strength. It's like a big tug of war within the molecule. If two sides are equally matched, the rope doesn't move. But if one side has a bunch of like jocks and one side has the chess team, no offense to the trope, but the chess team's going to lose. If the strength of the dipole is not equal throughout, one side gets run over. One side gets pulled out the other. So dipoles can be added or subtracted from each other depending on their vector coordinates. X can only subtract from X. Y can only subtract from Y. Z can only subtract from Z. So if I have someone pulling in the X direction and one pulling in the Y direction, they are not affecting each other. They create a new vector that is both X and Y. If two guys are pulling, one guy's pulling northwest and one guy's pulling northeast, the object is going to move north. So you got to remember, you can only affect things, they can only additive or subtractive when they're in the same dimensionality. Now, if a polar bond is arranged symmetrically around the center, the net result is a canceling of all bonds and results in a non-polar molecule. It does not matter if each bond itself is polar. If they are the same strength and they're pulling in opposite directions, they cancel out. CO2 is the perfect example. We have a strong carbon-oxygen double bond, but it's matched by a strong carbon-oxygen double bond pulling in the opposite 180-degree direction. Bonds, unlike people, do not run out of energy. They do not get tired. So the bonds will stay like that in a perpetual neutral state forever. unless some outside force helps them one way or another. So they will not suddenly become polar. Now, if polar bonds are arranged asymmetrically, they will result in a molecular dipole. And if there's a molecular dipole, we call that molecule polar. The examples I have, all the top structures are asymmetric by nature, and so their shape gives them a strong dipole moment. The arrows are pointing towards the positive side. So the first structure is HCl. The H is far less electronegative than the Cl, and so in a perfectly linear molecule, the Cl does not have anything opposing it on the other side, and so the H gets pulled, the electrons of the H get pulled towards the Cl. In water may have two oxygens down, but there's nothing up. And so the net effect is, even though there's oxygen on the left and oxygen on the right, there's nothing above them, and so the net dipole is up towards the oxygen. We have a structure over here that's CH2Cl2. We may have two H's opposing two Cl's, but the Cl's are stronger than the H's. We might have a Cl going up or Cl going down, but since they are not opposing each other, they're not imposing each other in the right direction. They're both pulling up and they're both pulling to the right. The net dipole is to the right. Now, the bottom structures here are nonpolar because of symmetry arguments. You can see right here, even though you may want to say that, oh, this guy is CO3, 2-, carbonate. Even though you might want to say there's a double bond here, the idea is that because of the resonance structure, the net effect is each oxygen is identical. And so even though we have one pulling up and two pulling down, technically the guy pulling up is pulling straight up. So it's 100% in the Z direction. This guy, oxygen on the left, is pulling down and to the left. So it's 50% in the X, 50% in the Z. And this guy on the right is pulling to the right, 50% in the X and 50% in the Z. So these two oxygens countermand each other in the X, and two 50% countermand this guy who's 100% in the Z. So they perfectly neutralize each other out because they are all counterbalanced. It's perfectly symmetrical. This guy's a lot easier to see. Carbon dioxide, it's pulling here, it's pulling there, they counteract. In a SF6 scenario, 6 bonds. This is octahedral. Each SF bond is itself very, very strong. However, because of the symmetry, they all cancel out. If you look right here, this guy is perfectly canceled by this guy. This guy is perfectly canceled by that guy. This guy is the up guy is perfectly canceled by the down guy. I want to go back to our structures real quick. This will be the last thing I'll do. Structures, and let's look at the symmetry and their polarity. Each bond itself on the xenon tetrafluoride is polar. However, this guy is canceled by this guy. Directly opposite. This guy is canceled by this guy. This guy is non-polar. What about the chlorine, the T shape? This guy is canceled by this guy. But this fluorine is opposed by 2 lone pairs. 2 lone pairs do not fight an atom. The atom always wins when compared to a lone pair. So the net dipole is this way. We would say this atom is partially negative, and this part of the atom is partially positive. A net effect of a polar molecule. Let's look at our trigonal planar down here. Let me redraw this. This guy is not symmetric. It's not symmetric because we may have, it's symmetric with a mirror plane like this, but it's not symmetric with a mirror plane cut it in half. Kind of like that, or kind of like that. So this bond is polar. These bonds are not polar. Since this guy is strong and these guys are weak, we have a net effect of a dipole pulling straight up. So that oxygen is partially negative. This carbon and these hydrogens are partially positive. Same thing here. We may have 3 atoms here, but P is a little bit stronger than they are. A little bit stronger than they are. So if we had a dipole, it would be pulling up like here. I'm not sure we actually do have a dipole, but if it does, it would be pulling up in that way. Straight up through that center. Partially negative, partially positive. But so that is where we will stop talking a little bit about polarity.